Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is a video on bias and variance uh, as part of the course Analytic Methods for Lawyers. The main problem with bias and variance is that the terms are very confusing. The concept's really important, but the names are awful. Really, what you should be thinking about is bias is a lack of flexibility or a lack of universality. That is, you can't actually compute certain things with a model. And variance is a lack of replicability or robustness. So both bias and variance are bad, both terms and things to see. And you want flexibility or universality and replicability and robustness. But nobody asked me, so I'll be using the terms like everybody else. And the idea is, again, you want your model that you develop through machine learning to be able to fit lots of forms of data, but not be so prone to chasing noise that they don't replicate well.
I'll also be discussing the Akaike Information Criteria, which is related to the issues under consideration here. Let's start with regression to see the issue. I think that's the cleanest way to go about it. And I'm going to divide my talk into these categories. Let's start with creating some data. All right, so we've seen things like this before, but let's just run through it. We've got the truth, which of course we don't know, otherwise we wouldn't be going through this process. But here's a function. It's a cubic with an exponential term and then heteroscedastic noise that could be pretty significant. So let's evaluate that. And now let's create some x values that run from -10 to 10. We'll create 20 of them, seeding our random number generator. And then we'll use a function. I don't know if we've done much of pair map before, but it's a fantastic resource function. And what it does is it takes a function f and some data, and it forms these pairs. x1, f of x1, x2, f of x2, x3, f of x3, etc. Let's run it. And there we go. We've got our points. We can see what our points look like here using listplot. All right, and there are the points. And we're going to try and fit some sort of model to that. All right, let's talk about how we create the models. Well, we've seen this before. It should be a nice review. We're going to make a table of potential basis functions. You'll see, like here, this is the simplest basis function there is. There's no x involved. Now, this is linear regression, quadratic regression. Now we've added a cubic term, a quartic term, quintic term. Now I don't know what these are called, but we're going to go all the way up to a 15th degree polynomial. So we've got 16 different sets of basis functions here. And now let's map a linear model fit over those basis functions, and what's going to change each time are the basis functions. The points stay the same, the variable x stays the same, but we're going to run 16 different regressions, and those will be stored in the variable LMFS. Lumphs. All right, and there are our 16 models. And what we can do is we can create a little animation showing the points and the best fit from each of these models. And what you're going to see in just a moment is, right, so the model gradually is fitting this data better and better. It starts off, that's a pretty cruddy fit. Getting a little, now we're getting like a pretty good fit here. Getting a nice fit. And now you can see it's going through lots of the points. And by the time we get to a 15th degree polynomial, yeah, we're missing here by a little bit, but we're nailing those, we're nailing those, we're nailing that. Got that one and that one. This is a pretty nice fit. So, again, when the polynomial degree is low, our fits are pretty dreadful. Like that's a pretty dreadful fit. That's a pretty dreadful fit. Really not getting good. It's only when we get up here, I don't know, to like a 6th degree polynomial that we start doing pretty well. All right. Let's see how the models actually perform. Let's try to measure this performance. And what I'm going to do is I'm going to compute the sum of the squares, that's our friendly power total, of the fit residuals for each of the models, and I'm going to use logarithmic scaling on the y-axis, and we haven't seen this data range option before. This says that our models range in polynomial, in the degree of the polynomial, from 0 to 15. So if we plot that, I just fixed a bug. Remember there was an ampersand, an ampersand right there, but you don't use an ampersand, generally speaking, when you already have a function. Remember, this is function notation. This is another form of function notation, but generally you don't use both. All right, so let's fix that, and you weren't supposed to see that. So let's run it. Okay, and there we go. So what you can see is that for low-degree polynomials, the sum of the squares of the residuals are quite high. We start making great progress as we start increasing the degree of the polynomial. By the time we get to 7, we're doing pretty well. And then there's some additional diminution in the sum of the squares of the fit residuals as we increase the degree of the polynomial. And remember that every time we increase the degree of the polynomial, we're increasing the flexibility of the curve. It can have basically more wiggles. And so the problem with the low degree polynomials is they're biased. In some sense, they can't wiggle enough in order to hit all of the points. And as we give it more parameters, we can wiggle more, and we can therefore hit the points. If we do compute the R-squared statistic for each of the models, and we compute something called the adjusted R-squared statistic for each of the models, we're going to see the same story. You'll see that at low degree polynomials, our R-squared is pretty wretched, and it does go up, and by the time we get to, I guess, about an 8th or 9th degree polynomial, we really have a very lovely R-squared. Just so you know, the adjusted R-squared is sort of intended to take into account this issue of high degree polynomial sort of always being able to fit models, even though, as we'll talk about, the fit is not going to end up actually extrapolating well to new data. I do not believe the adjusted R-squared is a good adjustment. You can use it if you want, you'll see it if you want, but very often it grossly understates how bad your R-squared statistic really is. That is, you'll see a high R-squared, the adjusted R-squared will be somewhat lower, but really is sort of, it should be a lot lower. So the adjusted R-squared is sort of a half-hearted effort to deal with problems with R-squared. Okay, let's now see, so we've got these models, let's see how they perform on new data. And the idea is, we're going to use that same process we did before with drawing from a uniform distribution on -10 to 10. We will then use pair map to get these pairs, x of 1, f of x1, etc. And the only thing that's different from this code than before is I'm seeding the random number generator differently. All right, so we did that. And now let's see how our model does on the new data. And we're going to create a little animation again. And there's our new data. And you can see, like here's this high degree polynomial, and it's doing swell, but it's sort of missing these points. And then it is cataclysmically missing this point and that point, even though that is the best fitting, whatever this is, 12th degree polynomial. And if we go further, let's run this to the end, you'll see, again, we're suffering. We're not able to fit all of this data super well. That is, this curve was determined on other data. Remember that it was determined before using the training data. But now when we have new test data, which is drawn from the same process as before, it is sometimes missing in a terrible, terrible way. Whereas in our sort of low degree or intermediate degree polynomials, yeah, we're not doing great on this stuff, and we're not doing great here, but we're not missing in these drastic ways. All right, so that's sort of an eyeball look at the issue. Let's look at it a little more scientifically, and let's write a function residuals, which is going to take a function and some data, and it's going to map f over basically the x values of the data, and then it's going to subtract from that the y values of the data, okay? And if we have more than one function, which we can put in this list here, it will map that function, it will map residuals over all of the functions. So this is an example of polymorphic programming, which Wolfram language is very good at. Now let's piggyback on the residuals function and write another function called SSR, for sum of squared residuals, which takes a function and some points, it computes all the residuals, and then it computes the sum of the squares using the epic power total function. And SSR has the same polymorphic feature as residuals. You can give it a list of functions, and it will then map SSR over all the functions in that list. So now what we're going to do is we are going to compute the sum of the squared residuals of all of the best fit functions for those new points that I calculated, and we're going to plot it. And let's see if it looks basically like this plot, where the higher the degree of the polynomial, the lower the sum of the squared residuals, or whether it looks like something else. Perhaps you can tell from my tone of voice what's coming. All right, so what we see is it starts in the middle, it goes down, it seems to go down most at 6, and then it starts going up, and by the time we get to a 15th degree polynomial, it's gotten to be a really bad situation, which is what I showed you before, where we have this cataclysmically bad fit. So what this is kind of suggesting is that if you want your model to replicate well, you want one of these intermediate degree polynomials which has some ability to wiggle. That is, it has not huge bias, but it also doesn't chase noise as the high degree polynomial models did. But maybe we just had bad luck. Let's automate this process and not try it on one set of new data. Let's try it on 100 new sets of data. So I'm going to get an array that's 100 by 20 by 2. That's what this function here does, generate points. And so now what I'm going to do is I'm going to run generate points, seeding the random number generator with values from 1000 to 1099. And then we'll do my famous through terse dimensions thing so we can see a short form of the output. There we go. And we can see that indeed we do get a 100 by 20 by 2 array. Now, let's take the sum of the squared residuals for the 100 sets of data on the 16 different best fit functions. So we're going to get a 100 by 16 matrix of values. So row 47, column 3 will have the sum of the squared residuals for the third model, which is, remember, the quadratic model, for this 47th 20 by 2 set of data. And we're going to call that experiment. Here's the code that's going to accomplish this. Notice how nice and terse it is, as it were. And there we go. So we've got our 100 by 16 matrix. Now, what we're going to do is we're going to take the mean total sum of the squares, the mean of the total sum of squares for each of the 16 models, and we're going to see on average which model does best when we confront new data. We're going to do that mean through the array reduce function, which we've seen before, and then we'll just see our friendly list plot. So let's see if this here was a fluke and whether really usually it's like this up here, or whether perhaps this is typical of the results that one would expect to see. Ready? Here we go. And our result above was not unusual. It was pretty typical. And we're seeing that on average, a 6th degree polynomial does best. 9th makes a comeback. I think that's sort of more of a statistical fluke here. And then you'll see degradation of the fit as we get up into 12th, 13th, 14th, 15th degree polynomials. And so what you see is that if you want your model to replicate well, you don't pick the model necessarily that fits your training data best, because that model has chased noise. And therefore, since that different noise will be present in new data, it is likely to get things catastrophically wrong. Let's take another look at this chart. And this time, here what I did is I plotted the mean of the sum of the squared residuals. What I might want to do is to see a distribution of the sum of the squared residuals. And to do that, we're going to use something called a distribution chart. I do need to transpose the data. Have we seen transpose before? Let's see what transpose does. So here is a 2 by 3 array. Now I'm going to transpose it, and you'll see that the columns have become the rows, and the rows have become the columns, and therefore I now have a 3 by 2 array. And so for purposes of the distribution chart, what I want to see is not how each of the 100 rows were distributed, but how each of the 16 polynomials had their sum of squared errors distributed. So let's look at this. And what you see is, yeah, sometimes a first degree polynomial will do decently, and yes, sometimes a 6th degree polynomial on some of the data won't do so well, but by and large, on average, our 6th degree polynomial does best. And do you see this explosion here in the range of values? That's the variance. The model, yes, the 15th degree polynomial every once in a while does fabulously well, better than that 6th degree polynomial ever did, but it also runs the risk of doing abysmally wrong. And so what we have is an exhibition of high variance. The model, sometimes it replicates well, but you can't count on it. So that, in a nutshell, is bias and variance looking at linear regression to show the phenomenon. What I'm going to tell you in the moment is that I just use linear regression for convenience, and the principle extends to all forms of statistics and all forms of machine learning. Let's talk about the Akaike Information Criterion, and I apologize if I'm mispronouncing the gentleman's name. I looked on the internet for how to pronounce it, and there are like 5 different pronunciations, so I'm going to use that one. All right, so what I just did is a bit of a nuisance, right? I had to calculate 15 different polynomials, 16 different polynomials, and run lots of regressions. That could be very expensive. Isn't there some way to know in advance that, hey, 6 is going to be your best? And one way of approaching this, there are others, is through the Akaike Information Criteria. You might applaud or be sad, but I'm not going to derive how you compute it. What I'm going to tell you is that it looks at the good old log likelihood of your model. And the idea, remember, is the better the fit, the higher the log likelihood of your model when you're doing one of those maximum likelihood estimates. And so what Akaike basically wants you to do is maximize the difference between the log likelihood of your model and the number of parameters in your model. If you're going to increase the number of parameters in your model, Mr. Akaike, Professor Akaike, wants you to increase your log likelihood. And for weird reasons, you actually double that difference, but the concept's the same. You should also know that if you don't have a lot of data, which probably my 20 sample model is an example of, You need to correct the AIC through something called the corrected AIC, which has the Mathematica and generally universal abbreviation of AIC little c, and that's going to increase the AIC for models that you develop. One other footnote here. Although I've been describing it as a maximization, it's actually a minimization of the negative of these things. And so what you want to do is to minimize the Akaike statistic. But it's the same idea of what you're trying to do is good models have high log likelihood, but if you're only getting a high log likelihood by using lots of parameters, then maybe you haven't accomplished that much. You should also know that there's a cousin to AIC called BIC, which is the Bayesian Information Criterion. I'm not going to go into that in more depth here, except to tell you that as a practical matter, they seem to usually give about the same answer, so we'll do AIC. And all I'm going to show you now is I'm going to show you the AIC and the corrected AIC-C for all of our models, and you don't need it. Here's how you calculate it. It's a built-in property of a fitted model object is this AIC business. So what you can see is that the AIC in blue does best at 7, so we were kind of saying 6, it thinks 7, that's okay. And then it doesn't go up that much thereafter. Our corrected AICC also does best at 7, but then it really deteriorates more as you go up. And so probably our model is small enough that the AICC is sort of a better measure of the truth. But you know what you can do is you can start calculating these AICC or AICC values as you increase your model complexity, and then once you start to go up, you don't probably need to go any further. It's going to continue to go up, and you can stop. And moreover, you might be able to actually project, if you get these numbers, you might be able to project kind of where the AIC is going to hit its minimum. So, let's reach our intermediate conclusion. Bias has to do with the inability of the model to wrap itself around all the training points. The problem is that the function is insufficiently universal to fit perfectly. It can't emulate every function out there. For example, there's no line in the world that can fit any 3 data points in a 2-dimensional space. Yeah, there might be one set of 3 data points that it would just happen to fit, but otherwise it's not going to be able to fit it. And there's no parabola in the world that can fit any old 4 points. The functions, parabolas, are insufficiently wiggly to do that. They are biased, to use the terminology. Variance refers to the tendency of models with low bias and that approximate universality to predict in highly varying ways when confronted with new data. That is, the variability to wiggle lets the model be tricked into chasing noise that's not going to be there next time. And so it's going to come up with a bad model. And there's generally a trade-off between bias and variance. Again, those are the terms you need to use when you talk to other people. If you talk to me, you can use universality and replicability, and I'll be very happy. I just illustrated the problem of bias and variance with actually a statistical method, linear regression. I now want to show it to you with a machine learning method. It's hard for me to do this using predict and classify because those methods are so good that they make it difficult for you to muck it up by introducing models that either have excessively high bias or excessively high variance. But the neural network framework gives me much more flexibility, and so I'm going to use neural networks to illustrate it. But again, the principle of this applies whether you're using random forests, gradient-boosted trees, whatever. The more universal the function approximator is, the more it has the potential to chase noise, and the more likely you are to have problems of variance when you try to replicate. On the other hand, if you have a totally simplistic model, it may not be able to fit either the training data very well or new data that comes from the same process. All right, let's start. I'm going to create in this grand scheme of things, this is not very deep. There are models with hundreds and hundreds of layers, but I'm going to create one with 1, 2, 3, 4, 5, 6, 7 layers, and it's this alternating thing here of a linear layer and a ramp. A ramp, by the way, let's just look at we'll plot the ramp function. You can see why it's named this way. I'm going to go from -3 to 3. And basically, if x is negative, the function is 0. And if x is positive, the function just equals itself. So ramp of 3 equals 3. Ramp of -2 equals 0. And this is a nonlinear function. And for reasons we might discuss, oftentimes what you want to do is to riffle in these nonlinear functions in between your linear functions. All right, so we have a linear layer. This creates 20 nodes, 20 little computation functions. Then we'll ramp all of those 20. Then we'll take the output from the ramp and we'll run it through another layer of 20 nodes. Then we'll ramp that. Then we'll run it through a linear layer with 10 nodes. Then we'll ramp that. And then finally we'll compress it down to one value. And so that's how our chain works. We now have to tell the computer, hey, what's the input going to look like? And it's going to look like a scalar. And a scalar is just a number. And what kind of output do you want me to make? And I say I want you to produce a number. So that's our network. And here you can see a representation of it. Input with 1, it gets blown up by the linear layer to 20. We ramp it. See what a nice ramp picture? Keeps it 20, ramp it, keeps it 20, compress it down to 10, ramp it, and then compress it down to 1, and you end up with the output. All right, so now I think I've mentioned that the machine learning functionality in Wolfram language wants the data in a different format than the statistics functionality, at least for now. And so we're just going to turn our points into a bunch of rules here. I'll let you see it, and then I'll suppress the output. All right, so instead of these being in a list, it's just an arrow. It's just a rule. All right, now you don't see it anymore. So now let's train the network, and here's our architecture. Here's the training data. This is telling it I want to know everything, and this, you don't need to know too much about it, except that I am actually controlling how it learns, how it adjusts its parameters, and I'm using some expertise and a little cheating here to do this. All right, so ready to see our network get trained? All right, so here it is, and you can see that loss just went way down. It just found parameters of the neural network that seemed to predict pretty well, and now it found some more, and we're doing better. We're at, and we're done. All right, so it did 10,000 rounds of training. It only had 20 examples because 10,000 times 20 is 200,000. That's how many basically computations it ended up with. And don't worry about the atom optimizer. All right, so let's see how this model fits the data. So trained net is actually a function. If you take a neural network and you look at the trained net property of it, that's going to produce a function. And we're now going to show our points, and we're going to plot that function, the neural network function, as x goes from -10 to 10. So we're going to take our trained network and plot the results, and you can see it's done a decent job here in fitting the data. Now, it didn't go down for those points, but it does seem to be capturing the idea here. So just as before, we computed the sum of the squared residuals. We can do that here. We can't get the sum of the squared residuals out directly, but we can get the mean of the squared residuals out. And if I multiply the mean by the number of points, then I get the sum of the squared residuals. So that's what I'm going to do. And I get 1.6 times 10 to the 6th as my sum of the squared residuals for this model. Okay, let's see how my model, though, performs on data it's never seen before. So all I have to do is take my old experimental data and put it in the right form for machine learning. There we go. And now I'm going to compute the sum of the squared residuals on each of the 100 sets of data. And there we go. And now I'm going to compute the mean of the sum of the squared residuals, and I get 5 times 10 to the 6. So let's hold that number in mind. Now, let's look at a smaller deep neural network. It's the same number of layers, 1, 2, 3, 4, 5, 6, 7, but instead of having 20 nodes and 20 nodes and 10 nodes, I've reduced the number of nodes by about 60%. Okay, so I've just changed the architecture of the network. I'm going to now use this new network, net2, to do the training. So there we go. You can see that wonderful moment where your loss function just dives down. Seems like not much is happening. Not much is happening. Just at the end there, we got a little bonus. And maybe that argues I should let it train for longer, but not at the moment. Let's see what this model produces. Remember, this is a slightly simpler network, and that's what it's producing. Again, it's not being snookered in by these points, and it's doing a nice job over here. We can compute the total error again. Or I'm sorry, yes. And now let's take the mean and let's see, what are we going for? When we had our more complicated network, we were going for 5.07 times 10 to the 6th. Let's see what happens here with our simpler model. And look, even though the model is simpler, it performs better on data that's never been seen before. Well, maybe we should get something that's even simpler. Let's cut out some of those layers. Here we have a 1, 2, 3, 4, 5 layer network, and not so many nodes. 5 here, 1 there. That's called net 3. Let's look at a picture of net 3. Same deal. We're going to train our network. This time, I do know this network takes a little longer to train, so I'm going to let it run for 20,000 rounds. If you think I'm being too nice to this network, just wait. So not much is happening. I haven't had that happy moment where the orange line dives for the bottom. Please, come on, could you do it just for me? Go, try hard, and no, it never really seemed to find anything. At least that's what my eyeballs are telling me. Let's see what kind of a model we get. So we do get a model that's sort of responding to the data. This is not a garbage model, but it's not quite capturing the subtleties that the other model did, but maybe it'll replicate well. Maybe its very simplicity, its lack of susceptibility to chasing noise will rescue it. So let's see, and let's compute this, and we're up at 1.58 times 10 to the 8th. We're not in 10 to the 6th territory here. And so this model is not wiggly enough. This neural network is not complicated enough to capture the complexity of the underlying data. And so what childhood story comes to mind at this point? It is Goldilocks, which really should be capitalized. You don't want it too hot, you don't want it too cold, you don't want it too tall, you don't want it too short, you want it just right. You want a model that's not too complicated, but not so complicated. Actually, that's not right. You want a model that is complicated, there we go, but not so complicated that it will succumb to the allure of noise. So I hope you learned about bias and variance and what that meant. You learned a little bit about which I can't, not only can I not pronounce it, I can't spell it, the Akaike Information Criteria. And again, This problem of bias and variance, it's not about just regression, it's not about neural networks, it extends to all supervised machine learning algorithms. Thanks for your attention.